SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering basic and applied. Today we shall discuss the flow through a steam nozzle. In fact, we have started our discussion on this topic in the last class, and if we can recall, in the last class we could derive the expression which relates the change in area or area Mach number relationship. So, that particular relation that we have established in the last class is known as the area Mach number relationship of a flow nozzle. So, if we try to write what we had derived in the last class. So, let me write flow through a nozzle. I should say the flow analysis, for the analysis we had discussed in the last class, we had to take a few assumptions. What are those? The flow is frictionless, both internal and external. There is no heat interaction between the system and surroundings. If we assume that the flow is taking place through the nozzle, then walls of the nozzle are insulated. We had considered that the flow is 1D, one dimensional, and we had also discussed that isentropic flow can be represented by an isentropic process. So, I am not going to write all those assumptions, but what we could write in the last class, the area Mach number relationship, that is 1 upon k into dP by P into 1 minus m square upon m square. So, if we give, this is equation number 1. So, this k is basically index of expansion for the isentropic process that we have mentioned, and we assume that steam flow is assumed to be one dimensional, right, and this is the flow or compressible fluid flow. Through nozzle. Now, let us discuss today a few important points. In fact, we can draw a few important conclusion from this particular equation. So, first we discuss about the physical significance of equation 1, because today we shall try to have the expression of the mass flow rate through the nozzle or through the convergent divergent channel, but before going to have this expression, have the expression of mass flow rate, let us briefly discuss about the physical significance of equation 1. Of course, concerning with the flow through a nozzle, not nozzle, rather if we try to write, in the last class we have assumed that it is the flow of a steam through a duct having varying area. So, it is the flow through a duct having varying area. So, 1 refers to inlet and 2 refers to outlet, right. So, now case 1 that we will discuss is the accelerated flow. So, accelerated flow of steam through a duct having varying area, cross sectional area. It decreases initially, then finally again increases. So, if the flow is accelerated flow, then if we just draw accelerated flow, that means we have understood, we have learned from fluid mechanics course that in the direction of flow, flow velocity will increase. If that is the case, let us look into this particular configuration. So, maybe if we are considering this is the case, so this is, say this is P1 and this is P2, right. So, when the flow is accelerating, that means velocity will increase in the direction of flow. So, P2 is much less than P1, right, and dP by P is negative. So, in the direction of flow, velocity will increase, pressure should fall, and it implies that dP by P should be negative. If dP by P is negative, now if we recall the expression, that is dA by A equal to 1 upon K dP by P into 1 minus m square by m square. M is the Mach number. Mach number equal to C by A. So, that means the local fluid velocity at any particular section at any particular pressure and temperature to the local sonic velocity at that section at that pressure and temperature. So, this is the ratio of the flow velocity at any particular section at any given condition to the local sonic velocity at that section at that pressure and temperature. So, this is Mach number C by A. What we have understood, if the flow is accelerated flow, dP by P is negative. If dP by P is negative, you can understand the area also dP by P is negative, that is true. K is index of expansion for the isentropic process. Now, the role would be played by the Mach number. So, now I am discussing sub cases, say when Mach number, so sub cases A, when C is less than A, that means Mach number is less than 1. If Mach number is less than 1, you understand dP by P is negative, Mach number is less than 1. So, to balance this equation, dA by A should be negative. So, this is the consequence of so this is what we can write. So, that means what does it indicate? If the flow is accelerated flow, if the local velocity at any particular section is less than the sonic velocity at given conditions, then we can see for this particular case dA by A must be negative. It indicates that it is a flow through a nozzle. So, this is the flow through a nozzle, the flow through a nozzle, right. So, in other words, this part, right, this corresponds to the convergent part of the nozzle, convergent part of the channel, right. So, if we go back to the previous slide, so this is a channel having varying cross sectional area. Now, if we look at this particular case, this case corresponds to flow through the convergent part of the channel, that is the nozzle. So, this is up to here, right. Okay. So, if we go to the next sub case, case B, right. So, case B, when C equal to A, that is Mach number equal to 1. When C equal to A, that means local fluid velocity, the velocity, local fluid velocity at any particular section is equal to the sonic velocity at that section, at that particular condition, that is pressure and temperature. Then what we can write? This is the accelerated flow, right. So, dP by P is negative. So, to balance this equation, m equal to 1, so this is 0. So, we can see this A equal to constant, right. So, this is m equal to 1, then A equal to constant, A equal to constant. So, it means that when m equal to 1, throat of the nozzle is reached. Perhaps you have studied these aspects when you have studied the compressible fluid flow part in your fluid mechanics course. You have seen that when m equal to 1, that is Mach number equal to 1, you can say that the flow has reached at the throat of the channel. So, this is case B, and last case of this particular part is, that is accelerated flow, is the C. So, let me write here using different other colors. So, that is this color. So, C, that is the when C is greater than A, that is Mach number is greater than 1. If Mach number greater than 1, if you look at the equation, so this is negative, dP by P is already negative because this is the case, flow is accelerating. So, what would be the consequence? dA by A is positive. So, that means we can write then dA by A equal to positive, that is obtained from the, so to balance equation 1. Right. if dA by A is positive, that means area increases. So, that means it is the, this corresponds to the divergent part of the channel. Right. So, this is the divergent part of the channel. So, that is the convergent divergent channel. So, we had considered flow through a channel having varying area. So, 3 different cases we have considered. Now, let us look into another important case, that is case 2. So, that is case 1. So, this is now case 2. Case 2, that is the decelerated flow. Decelerated flow or retired flow. Retarded flow. In that case, what would be the case? So, you can understand flow is decelerating. So, that means in the directional flow, if you write, so I mean if we consider a case, so in the directional flow, right, velocity will decrease. This implies that dP by P is positive, right. So, this is the case. If dP by P is positive, let us again write the area Mach number relationship, dA by A equal to 1 by K dP by P 1 minus m square by m square. M is the Mach number. So, let us now discuss about several cases. Say first case, sub case is A. Right. So, when C is less than A, that is Mach number less than 1. If Mach number is less than 1, this quantity is positive, that is there in the bracket. Now, dP by P is positive, that we can see from this particular case. So, when C less than 1, this m less than 1, this is also positive, dP by P is also positive, it implies that dA by A is positive. That means, this corresponds to the divergent type. This corresponds to the divergent part of the channel. Let me tell you, I am writing here, that is diffuser. See, when velocity decreases in the direction of flow, it is not a nozzle, it is the diffuser, that by definition we know. So, diffuser is again a mechanical device and the flow configuration is such that in the direction of flow velocity will decrease, pressure will increase. So, that is dA by A, that we can see. Now, let us discuss about another 2 sub cases, that is when C equal to A, that is Mach number equal to 1. If Mach number equal to 1, then dA by A equal to 0. So, it indicates that A equal to constant. right, and this corresponds to the throat of the diffuser. I am writing channel again, stroke diffuser. Now, that means if the flow is through a channel having gradually increasing area, then also m equal to 1 is the case when throat is reached. So, now the case last sub case is C, that is when C is greater than A, that is Mach number is greater than 1. What we can write? See, if Mach number greater than 1, this quantity is negative, dP by P is positive pertaining to this case. So, dA by A will be negative. So, we can write dA by A is negative. So, this corresponds the convergent part. So, this is essentially to balance equation 1, and this corresponds to the convergent part of the channel or diffuser. So, that means the diffuser should be of convergent type. Simply we can say, if this is the case, then diffuser would be of convergent type. Okay. So, now these are the case. If we try to summarize, basically you know that we have discussed several cases by considering several values of Mach number, several regimes of Mach number, that is whether Mach number is greater than 1 or less than 1 or equal to 1. For two different cases, in one case it is accelerating, other case it is decelerating. So, now question is, if we try to summarize just in the form of a table whatever we have learned. So, let us write like this: type of flow, right, then accelerated flow, that is falling pressure, and finally we have another category, that is retarded flow, rising pressure. So, we can see now type of the flow is say subsonic. Let me write here using different in another color. So, subsonic flow, that is m less than 1, right. If it is subsonic flow, we have discussed if the flow is accelerating, then this is the convergent part of the nozzle. Let us go into the first case. Accelerated flow, subsonic flow, that is m less than 1, that is the convergent part of the channel. What do you mean by convergent part of the channel? We do understand if the channel is having convergent shape, that is by common name known as nozzle. So, this is the nozzle. So, let me write here. So, this is the convergent channel, or I am writing nozzle, right. So, that is this is the flow direction, right. And if the flow is subsonic, for the retarded flow rising pressure, we have seen here that it is the divergent part of the diffuser. So, divergent part of the channel is that itself is the diffuser. So, I am writing divergent diffuser, right. So, this is the case, this is the flow direction. Arrow indicates the direction of flow. Now, if the flow is supersonic, that is m greater than 1. If m greater than 1, we have seen from case 1, when m greater than 1, that is the divergent part of the channel, divergent part of the nozzle, right. So, basically we can say that is divergent nozzle. So, this is divergent nozzle and this is the so this is the flow direction. And when the flow is supersonic, pertaining to this case, that is retarded flow, we have seen that this is the convergent part of the channel or diffuser. So, this would be convergent diffuser. So, this would be convergent diffuser and the shape would be like this. So, this is the flow direction. Now, last one is the sonic velocity. So, last one is the sonic velocity. Sonic, that is m equal to 1. Right. So, that is what we have seen, A equal to constant, okay, at the throat of the nozzle. So, that is the this part, area is equal to constant, and this is also A equal to constant and at the throat of the diffuser. So, this is the flow direction. So, this is what we have discussed. We have summarized in the tabular form what we have discussed pertaining to this particular equation that we have derived in the last class. So, now having this discussion, let us now. So, what we can see that if the flow is subsonic, if the duct is convergent, we can see, we can tell something else, something more from this particular table. So, if the flow is subsonic, duct is convergent type, then it is definitely nozzle. If the flow is subsonic, duct is of divergent type, it is diffuser. So, the word I have written convergent nozzle and divergent nozzle, because we have seen, we have studied that nozzle we call a channel as nozzle when its area decreases in the direction of flow. Even then I have written divergent nozzle. So, basically it indicates if the flow is supersonic, if the duct is divergent type, then so basically for the subsonic flow, if the type is duct is convergent type, it must be nozzle. If the flow is subsonic, duct is of divergent type, it must be diffuser, that we can see. If the flow is supersonic and duct is convergent type, it is diffuser. So, just opposite, if the flow is supersonic, duct is of convergent type, it must be diffuser. If the flow is supersonic and duct is of divergent type, it is the nozzle. So, basically flow is supersonic, duct is of divergent type, it must be nozzle. So, just the reverse, but for the sonic velocity it is obviously the nozzle is the throat is reached. So, with this I have completed the physical significance, rather we have tried to discuss about the physical significance of the relation, which is also known as the area Mach number relationship of the nozzle when there is a flow of steam through the nozzle. So, now let us look into the mass flow rate of the nozzle and whether we can find out the, because we have seen that our objective should be to get the what would be the area at the exit of the nozzle, so that the velocity of steam, desired flow velocity of steam can be attained. Now, to understand what would be the velocity at the exit of the nozzle, let us now try to look at the expression of mass flow rate through the nozzle. Let me tell you here that instead of the volume flow rate, we are referring to the mass flow rate, because we are considering flow of steam and which is considered to be the compressible fluid. Now, so basically you know that from the last part we have seen that the effect of same duct. So, it is the convergent duct, it is behaving just like a nozzle when the flow is subsonic. The same convergent duct can be used as the diffuser when the flow is changing from subsonic to the supersonic. So, let me write here one important conclusion, that the effect of same duct may be reversed depending on the behavior of the fluid and flow. So, this is very important. So, we can use the same duct sometimes as the nozzle, sometimes as the diffuser. Okay. So, now let us discuss about the mass flow rate through the nozzle. So, mass flow rate through the nozzle. Okay. So, again we considered the flow through a nozzle. So, this is outlet, this is inlet. 1 refers to inlet, 2 refers to outlet, and we are again considering the same set of assumptions that we had taken to establish the area Mach number relationship. So, that is the flow is one dimensional, there is no heat interaction between the system and surroundings. So, when there is a flow of steam through the nozzle, there is no heat loss from the flowing steam through the walls of the nozzle to the surroundings, frictional effect is neglected. So, considering all these assumptions, let me write again 1D flow, right, then no heat transfer, and frictional effect is neglected, right. So, we can assume, we can model the flow by the isentropic process, isentropic flow process and steady state. Steady state analysis, right. So, if that is the case, and if we apply the steady flow energy equation between section 1 and section 2, right. So, if we write the steady flow energy equation, so if we apply the steady flow energy equation, between section 1 and section 2. So, that is the flow direction. Okay. Then what we can write? We are assuming that there is no heat interaction and work interaction. So, we can write H1 plus C1 square by 2 plus GZ1 equal to H2 plus C2 square by 2 plus GZ2. You can understand that while we are writing this equation, we have not considered heat and work interaction. So, because there is no heat interaction, that we have already assumed, and this is not a work interacting device, but you can argue that of course, because we need to have some work, we need some work to maintain the flow in the presence of pressure. So, and that work done is already taken into account in this particular term, enthalpy. So, what we can write, if we assume that nozzle, the length is very small. So, if we assume the length of the nozzle is L and which is very small, then we can ignore even there is little elevation difference, but if the length is very small we can ignore the change in elevation, that is Z1 minus Z2. So, what we can write from this equation is that we can write, if we go to the next slide, we can write C2 square minus C1 square by 2 plus H2 minus H1 equal to 0. So, we are assuming here that length of the nozzle, short length of the nozzle right. So, elevation change can be neglected. So, in the last class I have mentioned that nozzles are placed in a plane where the elevation is very small, even there is a small elevation change between these two sections, that is inlet and outlet of the nozzle. Since the length is very small, we can ignore the change in that. So, that is why the change in elevation change can be neglected. So, we can write from this equation is that C dC plus dH equal to 0. So, say this is equation number 1, right. So, this is equation number 1. Now, we have discussed that, either we have learned from thermodynamics, for any process at any state point we can write, for any process at any state point we can write TdS equal to dH minus VdP. So, this is the second TdS equation that you have learned from basic thermodynamics course. Now, this we can write for any process. In fact, we also can write TdS is equal to du plus Pdv for any process. So, for any process this equation can be written at any state point. Now, the question is, we have assumed, rather we have tried to model the flow by an isentropic process. So, since the flow is modeled by an isentropic process, so we can write dH equal to VdP, so dP by rho. So, we can write, since the flow is modeled by an isentropic process. So, now what we can write, dH equal to dP by rho. If we give name of this equation is 2, if we use equation 2 in equation 1, we can write CdC plus dP by rho equal to 0. So, that means on using equation 2 in equation 1, we get this, right. So, this is what we are writing. Now, we can again we can integrate this equation from state point from section 1 to 2, then we can relate the change in velocity of steam as it moves from the inlet section to the outlet section of the nozzle. So, eventually we have this equation, and if we try to integrate this equation, we can write the change in velocity of steam as it moves from section 1 to section 2, and we can relate in terms of the pressure and density. So, from there we can at least get the expression of velocity at the exit of the nozzle. Why we need to have the flow velocity at the exit of the nozzle? Because we are trying to figure out the expression of mass flow rate through the nozzle, and the mass flow rate of nozzle which is important at the exit of the nozzle. See, mass flow rate at the exit of the nozzle should be density, velocity and the cross sectional area. Now, the velocity at the exit of the nozzle is very important, because that velocity will dictate the energy of steam that we are having before it strike the turbine, before steam strikes the turbine blades. So, that is why it is very important. So, we shall again process from this equation, that is integral 1 to 2 CdC plus 1 to 2 dP by rho equal to 0. So, that we can write, or we can simply take this in this form, integral CdC 1 to 2 equal to minus dP by rho 1 to 2. See, this is P, this is rho. So, what we need to do? We need to complete, we need to write the expression, we need to relate pressure and density. So, you know that P by, so basically we know that P V to the power k equal to constant, isentropic process. So, P by rho to the power k equal to constant. So, if we plug in the value of rho from this expression into this equation, then we can perform this integration and we can have the change in flow velocity of steam as it moves from the inlet section to the outlet section. And starting from this particular part, we shall try to calculate the mass flow rate of steam at the exit of the nozzle, and that part we shall take up in the next class. So, with this I stop here today, and we shall continue our discussion from this particular part in the next class. Thank you.